Talk about big data. As shown here in this slide, there is a lot of money in big data being spent at this time. So it is in your favor to know that. And so the question I'm going to do is, why big data? What are the different terms? What are the key technologies and databases? So now here is the thing. This particular lecture module is nothing about networking at all. Big data is actually databases. Okay? So this module is about databases. The next module is about networking. Alright? I cannot talk about networking until you understand the databases. Understand? And therefore, this is why it is called Big Data Fundamentals, is because we just want you to understand when I say SQL or SQL or Apache, Hadoop, this and that, you understand those terms. So this is that, right? So types of databases. And much of this is available in this book, which is designed for all of us, Big Data for Dummies. All right? However, there are many other books. All right, so what is big data? Data is measured by 3 dimensions. Volume, 3 V's. Volume, how many terabytes is it? If it is big, then it is big data. Velocity, how fast does it change? Right, terabytes per second. So if it changes very fast, then it is big data. Variety, what kind of data is it? Is it fixed? Is it text, audio, video, images, spatial, or mixed? The more problem there is, bigger problem it is, and then it becomes a big data problem. So these things were all there before, but previously the volume was very limited, the velocity was very limited, and the variety was very limited, because if it became out of our bound or out of our capacity to buy or to analyze, we said forget it, we are not going to analyze it, we throw away the data. But now what has happened is we have computers which are cheap, we have storage which are cheap, and we have networking which are cheap, and therefore we are increasing the bounds of these 3 dimensions. All right. Now these 3 V's these are old. I mean, this is not something that they discovered yesterday that we need to measure by 3 V's. When you think about it, they missed several things in here. First thing is location. So they never thought about that somebody would be analyzing data which is located in China, India, Japan, Korea, and USA at the same time. Right? That is not indicated by any of those 3 V's. So location is important, right? And churn. Churn is basically to do with somewhat related to velocity, but velocity in kind of indicates how often the data comes in, and churn is how often the data gets out of date. All right, and so that is churn is change, and then veracity. Veracity is accuracy. The data is very noisy. All right, so it's not perfect data. So how accurate it is, that also affects accuracy, correctness, applicability. All of those are put into this 1 V. So if you really think about it, the problem is bigger than 3 V's. And the examples of the data that we can analyze today that we could not analyze few years ago are social network data, who is connected to whom, what you are interested in, and so on and so forth. Sensor network data. So there are hundreds of sensors in the car, but you don't see any of those data because we just can't keep them, we cannot use them, do anything with them, right? But the next car that you buy probably will have all of that available for you and for the manufacturer. And so that is sensor network data. Internet search data. Obviously before Google, nobody knew how much information there is in the world, and now Google can analyze, if Google can analyze the whole world's web pages, then obviously the big data problem they have solved already, right? So that is search data. Genomics, and you heard about genome projects and things like that. Astronomy, the data coming from the sky. All of this previously was not analyzed, and not analyzed to the extent that we can do today. So these are all examples of big data problems. And in fact, we will see some more examples. But the question is, why are we doing our big data now? Well, there are 10 reasons why we are doing it now. First is, cost is low. Previously, we could not store a terabyte of data. By the way, I have a disk, a big disk, which was my first computer. It was 8 megabyte. Today, you won't even think about what is 8 megabyte. You won't even have a USB with 8 megabyte. You can't even buy 8 megabyte disk anymore. But that is how big the disk was, 8 megabyte. And then we went to gigabyte, and we felt it was too big, and then we went to 100 gigabyte, and now I carry 2 terabyte in my pocket, right? And so petabyte is common, right, for the companies. Terabyte is common for the people. So the cost of storage has gone so low that you can store anything that you didn't want to even keep it. Okay, so there's a lot of getting stored. Powerful multi-core processors. Computing is cheap. Low latency possible by distributed computing. So compute clusters and grids connected to high-speed networks. Now we don't just need one computer. We can use hundreds of computers together at the same time. Virtualization. And with virtualization, we can partition the resources. If we have too big, if we have too small, we can make it big. We can isolate it and dynamically change it. And so we can change it in any dimension. Affordable storage computing with minimal manpower via clouds. Second thing is, the manpower was expensive before. Now you don't need manpower because you can just give it to the cloud. Okay? And the clouds are all automated. Alan, are you with us? Okay, I'm with slide. Okay, they're not up on this screen. They're not up, by the way. All right, so possible because of the advances in networking. Now cloud is one reason. Better understanding of task distribution. So this is something that you will learn in this lecture, what happened to the ability to analyze all these things, and that is MapReduce and Hadoop. These things we didn't know before, how to analyze big data. Now we know. Advanced analytical techniques. Mathematically also we made sense with machine learning, for example. Before we didn't have those techniques. Big data platforms. So we have now cloud providers such as Amazon. They provide everything that you need to analyze. So even if you didn't want to learn anything about big data, you could just give it to Amazon. Not only they provide cloud, they provide big data analysis. So they will do everything. They will do Hadoop, MapReduce, everything for you. So nowadays you can just contract out cheap. So for example, Amazon Web Services provided Elastic MapReduce, simple storage service for storage, and HBase for database, which is a column-oriented database. Google provides BigQuery and prediction APIs and so on and so forth. So all of this is available easily. Open source software is the ninth reason. Is that nowadays you can get OpenStack, for example, which is the cloud computing software, or PostgreSQL, which is a database, all for free, all open source. All right? But the most important reason is the 10th one, because there is so much money in it. Last year, Obama announced $200 million for big data research. So suddenly all the professors are working on big data, including me. Right? When $200 million is there, we don't want to work on any other problem. Right? And $200 million was given to NSF, NIH, DOE, DOD, DARPA, and USCS. So anywhere you can get funding, it is there for big data research. So whether you are doing networking, whether you are doing computing, whether you are doing programming, whether you are doing biology, everybody is working on big data. All right? And I had slides there, but I removed them for you. Same thing is happening in the industry. The VCs are giving money for big data. So if you want to start a new company, you say big data, they say, oh yeah, here is the money. Right? So it's a hot topic right now. in the industry and in the academics. Okay, so now big data is used even for things that you would not have thought before, such as monitoring premature infants. So when a baby is born in the hospital, they put some sensors on them and the machine, just wiggles around and somebody has to see. Sometimes it says beep, 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 beep. But now we can record the whole thing. We can analyze it. And we can, before something happens, before it beeps, we can tell this is a problem, take care of it. So that is one thing. Predict machine failures in manufacturing. So before the machine breaks, we will know months in advance that this is about to break. Predict traffic jams. So before the traffic jam happens, they have these things which can monitor the traffic, cars and movement and everything is speed. They can analyze it at high speed, and so they can tell you, please don't take 360 or don't take 64 and go this way. Save fuel and reduce pollution. So every company, every enterprise is looking for use of big data because it is so possible now. I mean, in fact, you buy one thing from Amazon and then they analyze right away what are the other things that you looked at, and they send you a recommendation. Big data. Same thing, Facebook, whatever you do, every single move is being monitored and you get a recommendation. And every vendor, same thing. All right, now databases. So first thing when you go to database class, they teach you is that all the transactions have to be ACID. ACID stands for A for atomicity, C for consistency, I for isolation, and D for durability. Atomicity, that you don't want to do a transaction halfway. It's like this. Suppose you pay and you get a ticket, movie ticket. That's one transaction, right? Suppose you paid and then the machine failed. Would you be very happy that you didn't get the ticket, but the machine took from your credit card the money, right? So you really want it to be atomic in the sense that if they took the money, they should give the ticket. If they didn't give the ticket, they should not take the money. So the whole thing is just one thing, one atom. You cannot divide an atom. Now you can, but when the word was said, that time you could not divide the atom. So the thing is, all the transactions have to be atomic. Right? 0 or 1. You cannot have half of a transaction. Consistency. That basically it should be correct. If something is incorrect, then it will not affect the database, and the data goes from one valid state to another valid state, and that means whatever the validity means. Okay? So somebody cannot write things, for example, if the balance are supposed to be dollars, somebody cannot write it in pennies, or if they're supposed to be in US dollars, somebody cannot write in Chinese, and so on and so forth, right? RMBs. So the idea is they have to, whoever has the database defines some validity rules, and those validity rules have to be satisfied at all the times. Isolation. Multiple parallel transactions will not interfere with each other. So transactions are getting done all the time. When you have a database, there's not one user, there are hundreds of users. Right? And one user should not really affect, it will affect in some sense, but it will not really interfere with each other as much as possible. Here's the thing, suppose there is only one seat and two people try to get it, one will get it, and so this will affect the other guy for sure. But that is an expected outcome. Right? If both got it, that will be a problem. So other than that, there should not be interference of any kind. Durability. And once it is done forever. So if the output is written in the database, it stays there forever, even after the power loss, crashes, and errors. So you bought the ticket. Now if you go to the theater and they sorry, the machine crashed and we lost the whole thing, you would not be very happy. So you want that to be there forever. So those are the four things: ACID, atomicity, consistency, isolation, durability. And the database people go to a great extent to check that their database satisfies these requirements. And in particular, there was one variety of databases which became very popular, and this actually started at the time when I was in PhD student, relational databases 30 years ago. Relational databases, they provide acid, and then there were some databases that really didn't want to stick with acid, because acid means that you would be sacrificing something else. So they invented a new name called base. All right, you know the acid and the base. Acid is acidic and base is alkaline. So base stands for basically available, soft, and eventual consistency. All right, BASE. Basically available, soft, and eventual consistency. Because with base, you don't have to work very hard. Yes, there are some errors. Sometimes there is an error. For example, here's the thing you do on Amazon. You go and buy something, put it into the cart, and you say, now go and give my cart to me, sell to me. Say, oh, there's nothing in the cart. You just put a minute ago, and then what happened to my cart? It happens in Amazon. It happens to me many, many times. But they are not following acid. They are following base. So it basically doesn't happen, but sometimes it happens. Right? And if there is, you make it a 800 number call, and it is taken care of. All right, they will look it up. It may not be atomic. I made the payment but didn't get the book. Okay, so there is an 800 number for that. So for them, acid is not a good. I mean, acid is actually too much to pay for. So they have base. So everybody understand the pun? Base and acid, basically they are opposite of each other. Base, people do not care for the acid because acid requires too much work, particularly if you have a global database. There's lots of things happening in parallel. Okay? All right. Now, the data itself is of many different kinds. First is structured data. Structured data is one that has a preset format. Say, for example, your Outlook contact book. Every record in that one has a name, has a company, has a home phone number, right? But look at your web page and my web page. They are not structured. Yes, there is a structure. Everybody has a head and a body. But beyond that, you couldn't really find any structure beyond that, right? So that is unstructured. So structured is something where everybody has the same format. All the records in the database, address books, product catalogs, banking transactions, your checkbook. These are all structured databases. Unstructured are movies, audio, text file, web pages, computer programs, social media. These are not structured. Semi-structured, which is halfway between. And so, for example, you could take web pages and classify them into structured. Okay, web page, and then this is of whatever that is, right? Categories you put into them. So 80% of the world data is unstructured. That means most of it is unstructured. And so you have to worry about how to do anything with the unstructured data. And that was a big problem basically in the beginning. Most of the data, relational databases, for example, are designed only for structured data. All right. Then there is a batch data and the streaming data. Batch data is data that is comes and then you can keep it forever. Streaming data keeps coming. Your sensor data is streaming. You have some data, and then 1 minute later you have more data, and then 1 minute later you have more data. That is streaming, right? Real time. Some data is real time, and some is not. Real time means you have to really use it as it is coming. Otherwise, it's no good. Intrusion detection, for example. If there is an intrusion, you want to know it now and not tomorrow, right? If there is going to be an accident, you want to know it now, not tomorrow. Same thing for the other examples we had before, where failures, things like that. So those are real time in some sense, that you want to know them in time. This is also known as data in motion. So there is a data in motion and there is data at rest. So data at rest is more like data which can be analyzed any time. We can analyze tomorrow and makes no difference. Data in motion has to be analyzed right now. Or data at rest is next term. Non-real time, data at rest. Sales analysis, for example, you could sit down and analyze in the night as to what was sold and what we need to order. All right, that would be rest. Metadata. Metadata is basically the definitions of the data, the mappings of the data, the schemes of the data. So data itself is data, and then any things about it is called metadata. For example, if I have a class, I will have everybody's name, phone number, things like that. So those fields will be called metadata. Metadata includes name, phone number, and so on and so forth. But actual names is a data. All right. So let me see. Are these 6 terms clear to everybody? All right. So now we go into what happened in the last few years, and Google changed the world. Google changed the world by publishing 3 papers. And the first paper was Google File System. The reference is at the bottom. This paper basically said how to store big data, means how to store lots of data. And you know, Google has been storing the biggest amount of data, right? But unlike other companies that were doing it before, where they had big disks and, you know, big tapes and things like that, what they did was they just put some cheap PCs and put some disk on it. So this was all distributed. Because they are cheap, they will go down very fast, rather than having real high quality arrays like companies do. They had just cheap PCs with cheap disk in it. And so that was the thing. Google File System basically said we are going to use cheap parts, and therefore things are going to break, but we will keep 3 copies. So let them break, we will be able to make the copy if one thing breaks. So what they did was, they have these lots of computers, we call them chunk servers, and each thing that you want to store is broken into chunks, and some chunks are here, some chunks are there, some chunks are there, some chunks are there, but there are 3 copies of each chunk. If something breaks down, then a copy wherever it exists is replicated. So B4 break down, so we take a B4 from here, make a copy. Right? And if something is written, then we write it to all other copies as well. So if somebody writes here, then it is written to other places. All that is good. And there is one master server though. In addition to this chunk server, there is a master server, which is a central controller, which really keeps track of the whole thing. So this knows where B1 is. B1 is here, B1 is here, and B1 is here. Yeah.
If your master server goes down, do you lose the mapping of it? Like,
right, you will lose the mapping. But what you do is then you keep 2 master servers. So basically there must be a standby server. But for the time being, let's assume that there is one master server and it keeps the whole map. When somebody comes to write, they don't go to the chunk server, they go to the master server. Say, I want to write block B2. Right? And master server says, okay, go to chunk server 3. And then it writes B2, and then chunk server 3 also writes to other places. Yeah.
I have questions about what is the difference between this Google File System and the RAID?
RAID.
Yeah, RAID.
So there is very similar. It's just that instead of taking a RAID, they made a big RAID. This is big data. Right? So it's a very large scale. Yeah. I mean, in some sense, this is just a replication. Right? And this is a distributed replication. So for example, these 2 copies are in this rack, and this copy might be in over there, some other place. Physically also separated. So yes, the concepts were there, RAID were there, and this is, yeah.
Chunks are addressable.
Chunks is what you get. So basically, in the database things, you really don't go for little pieces. You just when you want to work on 2 petabytes, you are not going to ask for byte at a time. You say, okay, give me 64 megabyte. That's a chunk. Big. I think it's 64 kilobytes something. But anyway, so whatever size it is a big amount of data that you take once, and then you work on it, and then you get another chunk. Chunks are addressable. If your question is chunks are addressable, yes.
It makes
Yeah.
a difference from bit addressable, byte addressable kind of.
Yeah, right. They don't deal with bits and bytes. All right. So this is Google File System. And they basically, using that, they made a distributed storage system which they call BigTable. And BigTable was also published, and all of these papers are available on the Google website, by the way. And so what they do is they store the data in the rows and columns and so on and so forth. The main thing about this one is BigTable actually is not very critical, but I just wanted to put it here to be in the correct sequence, because this is all proprietary. BigTable is not available for anybody else to use. Okay? And since nobody else uses it, just I put some minimal information here. So the key thing about this data is that while if you have lots of rows, most of the rows might not have a lot of information because they might be empty. Okay, so sparse data. So this is designed for that. It is optimized for sparse. Sparse means mostly empty. Okay, and then they again use commodity servers, and this is not used outside of Google but accessible by Google App Engine. So Google has this API which they have published. If you use that API, you can use their table. Right? So first we saw a file system, then we saw a database system in some sense. Then they have a methodology called MapReduce. Again, this is another Google paper. And MapReduce said, how do you really analyze big amount of data? If you have 16 petabyte and you want to do it in a few seconds, how do you do it? Right? So you put 16,000 workers on it. That's the whole trick, is that you put a lot of people to work on this data in parallel. So you divide the problem into many pieces, and then you let everybody work, and then when they are done, you combine the results. That's all there is. Map and reduce. Map is distribute, reduce is combine. Okay? So distributed over large number of inexpensive processor, and everywhere their concern was that they really didn't want to buy very powerful. See, previous to this, people used to buy really big IBM systems to do database analysis. And these guys said, we don't want to buy any IBM system, we want to buy Dell computers or something like that. I don't think they buy Dell, but some cheap PCs. And so that is what it is that distributed over a large number of inexpensive processor is scalable, and the number of processor obviously is big problem, you give more, less problem, 4, 5, 10, 40, 400, 4,000, doesn't matter. So that is variable. Fault tolerant. And again, just like the disk, if you give it to 4,000, some will go down. These are cheap PCs. Right? So you ask two workers to do the same thing. If one goes down, the other one will bring the result. If both of them go down, then you ask third one to do later on. And so on. So that is what it is that basically redundancy is there. So map is to take a set of data and convert into another set of key value pairs. So basically, most of the data is organized like XML. I don't know how many people have seen XML. In XML, you have keys and the values, keys and the values, keys and the values. Right? So the database is organized like a key value pair, and you just take some keys. You say, well, all right, everybody whose last name begins with Jones, you analyze it. Everybody whose last name begins Smith, you analyze it, and so on and so forth. This key value pair, right? So basically, so the map divides it and then gives it out to lots of people, and then the reduce takes the output and produces the output. Obviously, there is redundancy everywhere, and so there are lots of mappers, and when the result is done, there are few reducers, two shown here. They reduce it, and then you get the output. Any question about MapReduce? Yeah.
The pair, what's the pair?
Key value pair. Key value pair. So, I mean, actually, a slide is coming later on where I showed some values of keys and pairs. But basically, here is the thing. Let's take your address book. In the address book, you have record number 1, some is Mr. Smith, age so much, gender male, income $10,000 or $100,000, something like that, right? So you could just write that as that the income colon 10,000. So that is the key and that's the value.
It's a pair.
And that's a pair. And then gender colon male, that's a value pair. Right? Then I could just take and tell him that, okay, analyze all the people whose gender is male. You analyze all the people whose gender is female. Key value pair. Then you can divide the database by any key values. All right. So here's an example actually. What you asked is just coming up. 100 files with the daily temperature in 2 cities. Each file has 10,000 entries. So this is big data now, because we took the temperature every second or so, and 2 cities. So for example, one file may have Toronto 20 and New York 30. That's the temperature. This is the city name, this is the temperature. And on and on and on and on. So the 2 sensors are sending us the temperature data and we are just putting it in the file. So these are the key value pairs. Our goal is to compute the maximum temperature in the 2 cities. Assign the task to 100 map processors. Each works on one file because there are 100 files. Each processor outputs a list of key value pairs. So this one goes and then comes out with all these 10,000 entries. It comes out with 2 values. It says, well, in this file, the maximum Toronto was so much, maximum New York was so much. Then the other guy goes and their file they see, okay, maximum Toronto was so much, maximum New York was so much, and so on and so forth. 100 people can do this in parallel. And then what we do? We take those 100 numbers and find out the maximum of those. That is the reduction process. Right? So, all right. So each of them outputs a list of key value pairs. For example, the first one could say Toronto 30, New York 65. Now we have 100 key value pairs now, right? At 200 in this case, with 100 mappers, right? We give this to 2 reducers, one for Toronto and another for New York. Toronto one will take the Toronto one and come up with Toronto 55, and the New York one will come out with 65. So that's your final result of going through so much work. Yeah.
Just so that we're clear, the mapping is parallel processing, and the reduce is aggregation of the...
Aggregation, but in this case, aggregation was also parallelized because the result was, parallelizable. Here we needed 2 cities, so we had 2 people working on it. Right? Some cases only one result you can have. Say for example, if it was all one city, then we'll have to basically, you could do in 2 steps of mapping, but I think you basically you just do it and then one reducer will reduce it to one number. In this case there are 2 cities, so that's why we have 2 reducers. All right, I think I will stop right here.